Welcome to lecture 48. In this lecture, we'll continue and finish our calculation of G minus 2. Recall that in lecture 42, we discussed that G minus 2 is related to the connected and amputated photon electron vertex. In lecture 46, we derived the result for this connected and amputated vertex in terms of an integral over Feynman parameters and a Euclidean integral of a numerator n mu and the denominator cubed. The explicit expressions for n mu and d can be found at the end of lecture 46. Note that this connected and amputated vertex is part of the full vertex, and the full vertex contains the external propagators. So basically it means that this connected amputated vertex in all practical cases is sandwiched between two free fermion propagators. So then there's an SMP, S underscore or S of momentum P, fermion propagator of momentum P to the right, and a fermion momentum propagator with momentum P prime to the left. Also note that we discussed one contribution from the numerator here, the one that is given by K slash gamma mu K slash in the last lecture, and we found that this contribution does not contribute to G minus 2. So basically, in this lecture here, we look at all the other contributions and we identify the ones that will contribute to G minus 2. If we disregard the one contribution proportional to momentum K, the contributions that are left in n mu that we have to deal with are the following ones. And the form of the denominator was given as K squared plus A, where A was this expression that we simplified for on-shell situations in the last lecture. If we now want to integrate the expression n mu by d, this is straightforward because n mu does not contain any dependence on the momentum k. And the denominator is just k squared plus a. So we have something that we can evaluate using this function phi from lecture 10. And we find it's given as 1 over 2 times 4 pi squared n mu over a. Part of the reason is that since this is 1 over k squared cubed, this integral is nicely convergent. So if you plug in the explicit forms of n mu, we find that the part of the vertex that can give contributions to G minus 2 is a form that is given here. It's still an integral over 2 Feynman parameters x1 and x2. And then we have a numerator and a denominator. In order to further simplify this expression, we now use the fact that the amputated vertex is sandwiched between the propagators to the right and to the left. In particular, if we consider that there is a fermionic propagator of momentum p to the right, if we have some contribution here that is a1 slash, it is acting on the s of p to the right. If we put in the explicit form of a1, that is just minus I x1 p slash plus I 1 minus x2 p slash prime acting on the fermionic propagator s of p. But we can simplify this because I p slash of s of p is just I p slash over I p slash plus m. If you plug in the explicit form of the fermion propagator, we can add and subtract m in the numerator so that we get 1 minus m times the fermion propagator. And the 1 here, since it does not contain this fermionic propagator anymore, will give a contribution that is something, but it's not a contribution that is a piece of the vertex. So this 1 here does not contribute to the vertex. This piece does because it's of the same form. So effectively, we can replace IP slash by minus m. And if we do this, then we find that A1 slash on SP is mx1 plus I 1 minus x2 p slash prime s of p. The p slash prime is the piece that is the momentum of the other fermion, and there clearly we cannot use the propagator here to simplify. However, we can start with this expression and look at the next term here, which is a gamma mu, and we can pull through the gamma mu through a slash, acting on the fermionic propagator, what we get is a term that involves the Kronecker delta. So we get twice P prime of index mu, and we have minus IP slash prime gamma mu. For the A2 slash, we can do a similar trick where we have the fermionic momentum P prime acting on the external propagator of momentum P prime to the left. And we can use this to replace P slash prime with M. So if we then write down all the terms, we find that this combination here is a series of terms that involves still a product of several gamma matrices. We can, again, simplify this expression by changing the order of the momenta such that all P slashes will be on the right, so they act on the propagator on the right and will be replaced by M's there, and all the P slash primes will have to be pulled to the very left and will then act on the fermionic propagator of momentum P prime and will be replaced by M there. And basically it's just a matter of keeping track of all the minus signs and the delta Kronecker deltas that appear by shifting the gamma matrices to keep up with all the terms that we get. So if we do this, then we get this following form here. And basically, yeah, so we find that there's an expression that involves all these combinations. And we can write those in the end as terms that involve a gamma matrix and the Feynman parameters and M squared. There's a contribution that involves P dotted into P prime and the gamma matrix. And there are two contributions that don't have any gamma matrices, but just have the momenta P prime and P. Okay, so after reshuffling these gamma matrices, we find that the numerator is of the following form. It has all of these contributions. We then use the same trick as in the previous lecture, where we replace P dot P prime as minus P prime squared, which is Q squared, plus P squared plus P prime squared. And we put this on shell. So then P squared and P prime squared are replaced by minus M squared respectively. So we get minus 2M squared. So we do this replacement for this term P dot P prime in here. And the other thing that we do is we replace P prime by 1/2 P prime plus P plus 1/2 P plus minus P, which obviously is the same. And we replace P by the same combination, but with a minus sign over here. So doing that, we find that the numerator can be written in the following form. And now has this Q squared here and this combination P prime plus P and P prime minus P. Next, we can simplify this expression further by noting that if we remember that there was this third Feynman parameter x3, which you can write it as 1 minus x1 minus x2. And that's useful because it turns out that this complicated expression here that's multiplying P prime plus P is actually simple when we express it in terms of x3. So we can write it as x3 squared minus x3. So if we do this, then the numerator has a simpler form. So again, collecting all the terms, we have that the vertex is given by the following expression. It's minus I e cubed over 16 pi squared, integration of the two Feynman parameters times the numerator and the denominator. And the thing that I want to point out next is that the denominator here is invariant under change x1 to x2. So we can change x1 and x2 here. This denominator stays the same. But if we look back at our expression for the numerator, there is this term P prime minus P. If we exchange x1 and x2 here, we get a minus sign. So that means that this contribution is odd under change x1 to x2, but everything else in the integrand is even. So that means that that term cannot contribute. So that term cancels out. The next term we want to investigate is the term that's proportional to Q squared here. Again, we said that the form factor that we are interested in is a piece that is coming from a vertex correction that is linear in Q. So here we have in the numerator a piece that's quadratic in Q. So clearly that piece cannot contribute to the form factor F2. So we can also neglect this contribution. And what we have left is now the following contribution for the vertex here. That is a contribution that's proportional to gamma, and a contribution that is just p prime plus p. And this x3 here, which really just means 1 minus x1 minus x2. So next we want to use the Gordon identity to replace this combination in terms of another gamma matrix and the spinor sigma mu nu with the linear momentum q nu. If we do this, then we already sort of know that the terms that's proportional to this sigma mu nu will be the one that is contributing to G minus 2, whereas all the other terms will give contribution, but not a contribution to G minus 2. So we find that after using this Gordon identity, the only term that will give a contribution to G minus 2 is this following term here. It's an integration of x1, x2, and this piece. And if we now recall from lecture 42 that the form factor we're interested in, F2, is the one that's well, basically what we did in lecture 42 was to assume that there would be a vertex correction that was of the following form, had the sigma mu nu, q nu, and this form factor F2. So we now find that this is indeed the case. We have calculated the contribution to the vertex, and this form really exists here. So we can compare these two expressions and find out the explicit expression for the form factor F2. So we find that the sigma mu nu is here, the q nu is there, and then the F2 form factor must be this integral here divided by this prefactor. What do we have? We have that the form factor F2 is given as e squared over 4 pi squared, integral over the two Feynman parameters x3 minus x3 squared over the denominator. We kind of use the fact that we have this nice expression of x3 here by reinstating an integral over x3 with a delta function. So we basically, this is just unity, so we can plug this in, and then we can actually change the orders of integration and do the integration of x2 first. So if we do this, we find the following form for the remaining integrations of x1 and x3. And why did we choose this route? We chose this route because we can now replace x1 in terms of 1 minus x3 times y, where y is a new integration variable. And if we do this, then we find that the x1 here gets 1 over minus x3 from here. There's a 1 minus x3 and another 1 over minus x3 in here. We can pull through the x3 in the numerator, get x3 times 1 minus x3 from the numerator. And there's another 1 minus x3 from the Jacobian. So all of these basically mean that the integration over x3 is such that all of the pieces 1 over minus x3 squared cancel, and we just have an integral over x3 of x3 itself that is just 1. And we are left with the integration over this factor y, which is given in the following form here. It's possible to do this integration, but for G minus 2, all we're interested in is the form factor evaluated at 0, photon momentum q. So we can just plug q is 0 into this formula, then this integral just gives 1, and we find that G minus 2, which is twice the form factor evaluated at 0, is just e squared over 8 pi squared times 2, so e squared over 4 pi squared. And we can write this in terms of the structure constant, fine structure constant alpha, which is e squared over 4 pi. So we have G minus 2 is just alpha over pi, 2 leading order in perturbation theory. Recall that fine structure constant here is approximately 1 over 137. And we can use this to do numerics. So we can express G minus 2 as twice times 1 plus a. And this factor a here then is alpha over 2 pi, which numerically comes out to be 0.00116141. And we can compare this to experimental values for the same value of a. A recent one is, for instance, 0.0011596521 and so on and so forth, where the measurement is accurate up to the last 2 digits here. And then comparing these two expressions, we find that our leading order perturbative calculation for the form factor, or G-2, agrees with the experimental result to essentially 3 significant digits. So this is basically one of the hallmarks of quantum electrodynamics as an example for a quantum field theory that lets you do very precise calculations of these experimentally relevant variables. We call that the calculation we've done is just a one loop calculation. So it's just first non-trivial order in perturbation theory. People have pushed this to much higher orders. Clearly, the calculation gets more complicated, but it turns out that one can get an agreement with respect to the experimental value to essentially 11 significant digits if one pushes the calculation that far. And that completes the lecture.